Hi. Welcome everyone to today's seminar. Today I'm happy to introduce Dr. Imogen Gingell, who is a Royal Society University Research Fellow based in the Space Environment Physics Group at the University of Southampton. Dr. Gingell gained her PhD in fusion plasma physics at the University of Warwick in 2013 and went on to join space physics groups at Queen Mary University of London and Imperial College London. Her research targets kinetic scale plasma processes, including instabilities and magnetic reconnection and turbulence, with a particular focus on the dynamics and energetics of collisionless shockwaves. I'm happy to have Imogen Gingell here with us today, who is going to be discussing this work and specifically magnetic reconnection at collisionless shocks. If you'd like to take it away.
Thank you very much for the intro there. And thank you for the invitation to speak to you today. I've been looking forward to it. I'm going to be talking about magnetic reconnection and how that relates to collisionless shockwaves today. So I'm going to take you through a few studies that we've been doing on that over the last few years. Before I get started, of course, I'd like to thank my various co-authors and collaborators who have appeared in the studies that I'm going to discuss today. So thank you all to them. So in terms of what I want to talk about, I know, often at these seminars, there's a range of experience levels. So I'm going to start off with just a little bit about the kind of the shock headliner, some of the basic motivations and some terminology to get us started. Then I'll be talking a bit about some simulations of reconnection of shocks and what we've learned from those, and then kind of pivot into the more observational sides of the studies and a couple of surveys of both reconnection in the shock transition and then a little bit further downstream in the sheath, and hopefully build a coherent picture for you of how all that works. I'll then finish off with some newer work, going back to look at simulations again, and round off on some of the conclusions. Okay. This is probably the sort of diagram that many of you have seen frequently before. I'm most interested in collisionless shockwaves, and of course the most accessible collisionless shockwave we have in space physics is the bow shock of Earth's magnetosphere. So that's kind of pictured in this cartoon on the right-hand side here. That is the transition where we move from a sort of fast, cold solar wind flow out on the left here to we cross this discontinuity, the bow shock, to a region where we have hot, slower moving subsonic, high density plasma in the magnetosheath here. So this bow shock is generated because the Earth's magnetosphere, I should say, is an obstacle moving through the solar wind faster than the local wave speeds, in this case, the fast magnetosonic speed, the Alphen speed, and so on. So this whole picture is really directly analogous to a sort of atmospheric shock wave. I've got here a shadowgram that was taken of the bow shock that can be seen at the front of a speeding bullet. So here we have our supersonic bullet here, and the kind of parabola shape of the bow shock at this bullet kind of standing off the front of the bullet, generating this nice turbulent wake as it goes through the gas here. So this kind of structure, of course, it's not just to do with the magnetosphere, although this is our most accessible one. We can look at different scales. For example, we see these kinds of structures in stellar heliospheres as well. So this is a visible light image from Hubble telescope showing the bow shock formed here in front of the star LL Orionis here as it moves through the interstellar medium. So just jumping back to this picture of this bullet and comparing it to the magnetosphere on the side here, one of the biggest differences between these two pictures comes from this, it's this keyword at the front of the top of the slide here. It's collisionless. So when we have a bow shock or any kind of shock wave in a gas, such as this bullet here, we can slow down and heat that supersonic gas across the bow shock by means of the fluid viscosity, the collisions between particles in that gas. In space, we don't have that luxury. The mean free path of particles close to Earth, for example, is about 1 AU by order of magnitude. So these particles are only really going to have collided with either none or 1 or maybe 2 if they're lucky particles over the lifetime since leaving the sun's corona. So when we cross this transition and slow our plasma down, we can't mediate that transition by collisions. Instead, we have to use electromagnetic interactions. And that kind of informs the general sort of big picture question of collisionless shockwave physics, which is to say, in the absence of collisions, what electromagnetic processes are going to be driving particle energization, heating, particle acceleration across that thin discontinuous region. And as you'll see in the slides I'm going to show you, new methods for doing that, we find them all the time, well, you saw in my title slide that one of those particular interactions I'm going to be discussing in the future is magnetic reconnection. That is a way to take energy out of the magnetic field and put it into the particles, which maybe can contribute to the energetics inside the shock. It may not be the most significant one, but well, you'll see in some slides that maybe it has a little bit more than a rounding error on the end there. A note on terminology as well. As I promised, I'm going to be talking a lot about the difference between quasi-parallel and quasi-perpendicular shocks as I talk today. This theta Bn parameter describes that difference and what that angle is that I'm referring to as parallel perpendicular. So this angle theta Bn is the angle between the normal direction of the shock surface and the upstream magnetic field. So for example, in this cartoon here, if we have an upstream interplanetary magnetic field line in blue, and our shock surface is the kind of difference between this gray and this red here. So out here we have a normal that goes in this direction, an interplanetary magnetic field in this direction, so that's perpendicular. And down here, we have the magnetic field is sort of parallel to that shock surface. And because of this difference in magnetic geometry, those two kinds of shock, quasi-parallel, quasi-perpendicular, end up looking very different from one another. So here is a cartoon and a bit of data to illustrate a sort of typical quasi-perpendicular shock. Now, these shocks in some ways are the most like those typical kind of gas dynamic shocks. They're very planar structures. They tend to have quite quiet upstreams and downstreams. And they follow this fairly clear discontinuous-ish structure that looks a bit like this. So if this black line is the magnetic field strength, we have this low field solar wind, rises very sharply in a clear kind of near discontinuous ramp where it peaks in an overshoot, comes down into an undershoot, and then kind of oscillates back and forth as you travel downstream into the magnetosheath. It also has this foot structure, which is where a lot of the interesting plasma physics, that kinetic scale plasma physics is happening in that shock. So this is the region where particles can kind of specularly reflect off this sudden sharp increase in magnetic field and travel briefly upstream and then kind of gyrate back and re-encounter the shock. So in this foot region is where you start to see a whole bunch of different plasma waves before you reach this overshoot proper. And we can see that in some MMS data here. In black is the magnetic field strength and the components here in the different colors. So you can see quiet solar wind, a bit of activity in the foot, sudden sharp increase into the overshoot across the ramp, a bit of kind of oscillation, and then you end up in a kind of more traditional magnetosheath down here. And this is just a bit of a zoom in showing those waves in the foot down here. You start to see the effect really kind of as early as over here, and the jump into the ramp, overshoot, undershoot, sheath. So as I talk through some of the rest of this talk, I'll be referring to a shock transition region. And for that, generally what I mean is the region of the plasma that is kind of clearly separated from the upstream solar wind, and something that looks more kind of undisturbed magnetosheath. It may still be turbulent in the magnetosheath, but you don't see these large scale oscillations. Okay, so that's the quasi-perpendicular shock. It's the most discontinuous, it's the thinnest, it's quite clear. The quasi-parallel shock is a whole nother kettle of fish. So the quasi-parallel shock, any particles that may be reflected at what would be a shock ramp, the kind of, if you figure out the geometry of those gyrating reflected ions, they may not re-encounter the shock again and instead simply travel upstream of the shock. So you end up with a backstreaming population of ions, of energetic ions, which can excite instabilities upstream of the shock, generating what's called a foreshock. So if we return to our little cartoon down here, we can see, in the quasi-parallel bar shock down here, you have this disturbed foreshock in the upstream region. And generally, even once you get into the structure of the shock wave itself, because of all this activity in the foreshock, you end up with a much more complex shock structure. So rather than having a kind of clear, planar shock structure, as in the quasi-perpendicular case, you end up with something that is a lot more patchy, made up of kind of short, large amplitude magnetic bursts, these slams and shocklets that gradually build up to something that can be kind of considered a kind of a more discontinuous shock wave over larger scales. So here is a good cartoon of what that looks like from Schwartz and Burgess et al. 1991 of a quasi-parallel shock transition region, or transition zone, they call it, where you're building up these kind of mini magnetic bursts where you can slow and reflect the plasma just in little patches, gradually building up to the sheath down here. So when we look at that in data, this is what it looks like. Gone are the days of that clear discontinuity and that nice foot structure and the nice ramp structure. It altogether looks much more messy. So you can see here, this is some more magnetospheric multiscale data with solar wind on the right, magnetosheath on the left. You can see in the ion spectrogram here that we have this thin solar wind beam here. But you get these high energy backstreaming ions up here. And you can see, even if you squint, there's no kind of picking out of one individual shock ramp in this particular case. So the complex structure here really drives a lot of study in the area of shock physics. How do these quasi-parallel shocks work in the absence of that kind of more traditional discontinuous shock structure in the quasi-perpendicular case. So that is where I come to this sort of the first study I'm going to show today, which was actually a simulation of a shock wave we did for a paper looking at non-stationarity in one of those quasi-parallel shocks. So we wanted to see, using a 2D simulation like this one, and I'll play this movie in a second, we wanted to see what that complex structure we saw in 1D traces, spacecraft trajectories like this, can look like, when we have the full picture from the simulation. So I'll just play this now. And you can see a couple of neat features in here. We have the inflowing solar wind on the left, the Magnetosheath on the right, and the shock is kind of in the middle around here. And you can see that you get waves in the upstream region that grow. Can I make that play again? There we go. Generating this very turbulent looking sort of transition region in the middle here, which generates a whole bunch of different structure, some of which survives downstream. So you can see these little closed magnetic islands still downstream when the shock ramp is kind of reformed here. So you can see from a simulation like this that the shock in the quasi-parallel case is both complex and time dependent. So you can see over a period, in this case of about 3 ion gyro periods or so, the shock completely changes its structure and regenerates in a process called cyclic shock reformation, which will become important a little bit later on. But one of the things that stood out to us in that simulation was how messy that shock transition region can get. And zooming in, taking a snapshot of that video and showing it on the right here, we've now plotted out these magnetic field lines as lines in black here. You can see we're generating some very interesting magnetic structures in here, like these ones up here. So we have current sheets like this one. You can probably see an example of one like here, where you have a kind of a next point in here. And flux ropes or magnetic islands in 2D like this one, which you can see these kinds of closed structures here. So given that we're generating structures like this, in a 2D simulation, at least, that implies that you must be having some sort of magnetic reconnection occurring. Otherwise, you can't close off those field lines to generate these kind of closed field line structures. So that, kind of opened up that kind of question in some of these future studies, how are we generating these current sheets and the kind of closed magnetic field lines? Can we see them in real data, or is this an artifact of the simulations? And then eventually, what impact is this going to have on our shock dynamics? So the first thing I'll show are some other studies which have kind of advanced our understanding in the processes that are involved in generating those reconnecting current sheets and closed field structures. I want to highlight this paper from Bessho et al. From 2020, which really goes into some fantastic detail in characterizing those fluctuations. And they found with another kind of quasi-parallel shock simulation, a kind of with these mid to high Mach numbers, they found much more detail in the mechanism that I showed you on the video just before. So this is the kind of middling Mach number case of about 6.5, and you can see the generation of those upstream waves in the foot of the shock, which can lead to a generation of that turbulent transition region. That's what they call a long wavelength mode, an ion scale mode driven by an ion-ion beam instability from backstreaming ions. Now, as you approach higher and higher Mach numbers, this kind of generates this turbulent transition region, which you can see much more clearly in some of these higher Mach number runs on the left side here, where those waves can kind of pinch off closed field structures like this one in here, this one in here. So that can lead to reconnection. And those reconnecting structures can then generate a kind of secondary mode where those electron outflows from the reconnecting structures drive a kind of excite Whistler waves, which in turn can drive a shorter wavelength mode for that reconnection to occur again. So you have this kind of separation of scales between electron and ion scales. I should note, though, that this is not entirely a quasi-parallel phenomenon. Here is a simulation I want to show of a strictly quasi-perpendicular shock. Well, not just quasi-perpendicular, but exactly quasi-perpendicular shock. From a paper by Matsumoto et al. In 2015 in Science. And they showed a slightly different mechanism, this time for an extremely high Mach number shock of 42 here. So this is on the extreme end of something you'd see at Earth, much more likely something you'd see at the outer planets, and exactly quasi-perpendicular. And they found that you could generate reconnecting current sheets and magnetic islands by means of an ion viable instability, which is generated by the sort of tangential propagation of reflected ions in the shock foot. And that leads to this kind of filamentation that you can see in this plot on the top here of the snapshot of this shock wave. And if you zoom in on one of those filaments in here, you can see it generates that kind of train of magnetic islands and reconnecting current sheets along one of those filaments. So that was kind of the simulation case that we've built so far. We have a number of different mechanisms that suggest that reconnection does occur in a kind of turbulent or disordered transition region inside the shock wave by at least 2 or 3 mechanisms. That is an ion-ion beam instability from the backstreaming ions generating those upstream waves, or this kind of secondary Whistler-driven mode electron scales. These two, both in quasi-parallel shocks, and at quasi-perpendicular shocks, we can get this ion viable instability. So the question is, can we see that in the real data? You know, it's all very well simulations showing it, but maybe it's just an artifact of the way those work. So we can have a look at our case studies, and we showed that indeed that does happen in real life. So here is a snapshot of one of the first case studies we had from our paper in 2019 in GRL, which showed one of the first examples of a reconnecting current sheet embedded in one of those shock transition regions. Here is the kind of overview plot from some MMS data, and you can see that the spacecraft transitions from the Magnetosheath through a shock transition region, kind of grayed out here, where you can see kind of a bunch of messy magnetic structure in here and field reversals, until eventually crossing a sort of a shock ramp and then out into the solar wind. We picked this particular shock as a good case study because it mimics some of the features we saw in that video of the simulation I showed you early on. And indeed, if we kind of zoom in on this kind of magenta line here and look at the next slide, we could see embedded in this transition region what looked like a reconnecting current sheet. So you can see here we've now transformed the field over these few seconds into a minimum variance coordinate system. So L is the max variance direction, N is the min variance direction, effectively the normal to that current sheet. So you can see in red the field reversal, positive to negative along that current sheet. You can see a Hall reconnection signature in this kind of bipolar signature here in the M direction. And if you blow that up, or if you squint and have a look in here, you can see an electron outflow associated with an active reconnection site. This is ongoing reconnection. So you can reconstruct what we think that looks like with the trajectory, and it looks like the spacecraft is moving along a kind of asymmetric current sheet embedded in this region like this, seeing this electron outflow on the bottom here. Okay, so what's also interesting, I should point out here, is that this appears to be an electron-only reconnection site, which has been of particular interest to magnetosheath turbulence over the last few years. Note that we have an electron jet here, but we don't have any kind of equivalent in the ion velocity, which it's the dashed line here. Okay. So in terms of trying to measure the energetics of a case study like this, we can look at, for example, J.E or J.E prime, which is a measure of the energy transferred from the fields to the particles. And you can see a bunch of J.E activity in the center of this current sheet here. And again, coincident with that field reversal and that J.E, we see some heating in our electrons here, you know, this nice little peak in the electrons. Nothing in the ions again, another signature of electron-only reconnection for this particular example. Interestingly, we find that this kind of few eV rise in the electron temperature is consistent with the expectations from empirical studies, statistical studies of magnetopause reconnection. So it looks like this is kind of in line for what we expect for a reconnecting structure. So it kind of ticks all the boxes there. It wasn't the only study showing this off. Shan Wang also had a 2019 GRL showing the kind of occurrence of a reconnecting current sheet in the transition region of a quasi-perpendicular shock, which I show in this figure here. The B field is here. You can see the reversal of the B field in blue, the Hall field and so on, some energy conversion in J.E, and kind of electron outflows here too. That's where we are at the end of this kind of summary slide mid-case study. We know that reconnection is occurring in some shock transition regions. We know that it occurs in simulations. So the next piece of the puzzle we asked ourselves is, okay, well, how common really is it? It's all very well picking out one or two case studies, even if those case studies do line up quite nicely with some of the empirical data, the empirical expectations. So what we did next was to perform a survey of a whole chunk of shocks observed by MMS. That is, we looked at all the shocks we could see in MMS's phase 1. That consisted of 223 available shock crossings. And then we went through each of the shock crossings and looked at all the reconnection sites or the reconnecting current sheets we could find in those particular burst intervals. So this was the process we used to narrow down our search. We took our list of 223 shock crossings from MMS's high resolution burst mode. In each of those, we calculated the current density from a kilometer method that's using the 4 spacecraft tetrahedron to calculate the curl of the field, which is then the current. We label up any regions of particularly strong current, that is where the current exceeds 3 times the standard deviation across the whole interval. Then for each of those high current regions, we perform a minimum variance analysis to transform from GRC into LMN coordinates. And then we check, well, does the max variance component flip from one direction to the other? Does it reverse over that current carrying region? So if we pass all those tests in blue, it gives us a pretty good idea that we've got a reconnection site. And then we ask this one more question, which is, do we see a peak in the L direction of the electrons, which would be the electron outflow? So this would tell us if there's an active reconnecting current sheet, if we have outflow. So we can do that on all our 200 shocks. That gave us these kind of 900 candidate events, which we then just sifted through manually, checking, do we see a good current sheet structure? Are the eigenvalues good, for example, from the LMN coordinate system? We looked for a clear peak in the electron outflow. And once we were satisfied, we cut that down to about 165 events. So the first thing then we ask ourselves is, okay, what kind of shocks do we see those reconnecting current sheets at? And this is kind of the statistics to do with that. The headliner is that we saw at least one reconnecting current sheet at 40% of the shocks that we were included in our survey. So it really does seem to be a common process. The next thing we had to look at was, well, how does it depend on shock parameters? So that's what these figures here are showing. In the top here, we have the parameters of all the shocks that were included in our survey. In the red is the distribution of shock parameters for only those shocks that included at least one reconnection site. And then on the bottom is the ratio of those two histograms, essentially. So if a point is above the red line, it means that that particular parameter range is overrepresented among the population of collisionless shocks that exhibit reconnection, and the opposite is true if it's below the red line. So this tells us that, first off, we see reconnection pretty much across the full parameter regime. So it really does appear to be a universal process. Second, there's maybe a slight kind of bias towards quasi-parallel shocks being more likely to exhibit reconnection, although it is fairly weak. Likewise, maybe it's more likely that we see reconnection at high Mach number shocks, although this does stay pretty level throughout the population of shocks that we see at Earth. Another thing that's interesting to look at is distance from the shocks. So, this is asking, well, where relative to the shocks do we see each of those reconnecting current sheets? And these are the results from that on the right here. So the top left panel here is the sort of time since we last crossed the shock ramp to when we see a given reconnection site, and this is the distribution of that. And we can see that mostly you see the shocks, the reconnecting current sheets close to the shock ramp. The bulk of them are very close to the ramp, and then it kind of decays downstream. There are about 12% of those reconnecting current sheets observed upstream of the shock, either in the shock foot, like these few here, or even a little further upstream still. We can convert that into a kind of pseudo distance, which is to just say, well, how fast was the shock moving over the spacecraft when we last saw it? How long has it been? That's probably how far we are from the shock. I call it pseudo distance because that assumption is quite weak. The shock probably won't keep going at the same speed we saw it past the shock, the spacecraft. Still, it gives us a pretty good idea, similar to this plot of time, that you see the bulk of the observations of the current sheets close to the shock ramp, and then it decays downstream. The red plot down here are an attempt to kind of remove some of the selection biases. So we're picking a whole bunch of different burst mode intervals, which naturally come with the selection bias of what the scientist in the loop chose. So if we take out a factor of how long the MMS spacecraft spent at any distance from the shock, we can kind of flatten out that a bit more. And we can see generally the statistics get a little bit worse, especially as you go further downstream where MMS doesn't spend much time. But you can still kind of see we get this kind of decaying, reconnecting region downstream of the shock. So the fact that we see quite a lot of shocks reconnecting current sheets in this localized region downstream kind of supports this kind of turbulent transition region mechanism generated by that ion-ion beam instability. So that kind of informed our next step in this. We saw those terrible counting statistics as we were going further and further downstream. So we thought, okay, what if we repeat our analysis for some magnetosheath intervals? See if we can't chart what that distribution of current structures is going to get us a little bit further downstream in the magnetosheath. So we performed another survey, this time of the magnetosheath. And this is really going to help us answer these couple of questions in this yellow box here. We know that the magnetosheath is also a turbulent kind of plasma. We expect to see some reconnection happening there. We've seen it in plenty of studies before, and I've highlighted only a couple of recent ones here. But maybe if we extend our survey down to the magnetosheath, we can look at how that turbulent transition region generated in the shock and any reconnecting current sheets there kind of transitions towards the magnetosheath. Does one smoothly evolve into the other? Are these entirely separate processes? Do you see, kind of a clear separation between the two? Let's have a look. So we did that using these 30 or so magnetosheath intervals distributed across the magnetosheath, even out into the flanks here. And we picked out magnetosheath intervals which have at least 20 minutes. So these are really very long sheath intervals to get the kind of the best statistics of current sheets we can. So this is an example of one of those current sheets. One of those sheath intervals. And we looked at, this is the B field at the top here, and you can see it's flipping back and forth, particularly in the blue, which is the Z direction in there. There are a lot of current sheets embedded in this particular magnetosheath interval. And if we perform that same kind of style of search that I showed you a few slides ago, check where the high current intervals and so on and so forth, we can plot this plot at the bottom here. So we now have that 3 sigma threshold as a moving 3 sigma this time. We pick out where all these black bars in the current jump above that line. And if they pass those various other tests, sort of the including like outflows or field reversals or good eigenvalues, then we highlight them in magenta here. So the magenta are the current sheets we like, or the ones we're pretty sure are current sheets, I should say. So then we want to kind of quantify the amount of current sheets that we see. We want to know the prevalence of current sheets, and we can do that using a couple of simple measures like this. We can say, well, what is kind of like the 1D number density, which is to say the number of current sheets per unit length observed in the plasma breast frame. Essentially, count up the number of pink magenta lines. We know how fast the plasma is moving. We know how long the interval is. that gives you your 1D density. Another way you can do it is to look at the volume of the occupied by the current sheets, that is sort of packing factor, which is simply, how long do you spend inside the current sheets in these pink bars relative to the total interval. So that's just this simple equation here. And if you do that and you compare it against distance from the shock and different shock parameters upstream of your magnetosheath interval, this is what you get. And alarm bells may be ringing in some of you now because you can see that these scatters are quite wide. The correlations are rather poor. We can see, generally speaking, you get fewer and fewer current sheets the further you go from the shock. Particularly, it looks rather good in the packing factor. So, these ones with distance are generally okay. But if you look at it, this is Mach number and shock orientation. You can see, these scatters are kind of all over the place, suggesting there's no clear sort of dependence of the prevalence of current sheets on the upstream shock parameters, which is surprising. So we thought, okay, can we do this better? And we sought a kind of a 3D method of working out what the kind of three-dimensional density of the current sheets is. And that's done by basically considering now a volume rather than a 1D trace drawn by the current sheet. Sorry, by the current sheet, by the spacecraft. So that volume is sort of an Alfvén cone. It's analogous to a light cone. It's the volume over which a magnetoacoustic disturbance could have traveled such that it would intersect with plasma that the spacecraft sees. And then the number is just the sort of, we look at some kind of heating or energization process across the whole interval, this kind of the change in temperature or the integrated J dot E. And then we look at the mean change over each of the individual current sheets that we do observe. So either the inflow magnetic energy or the integrated J dot E per current sheet. And by looking at the average compared to the total change, that tells us roughly how many we might expect in that volume. There are a number of caveats associated with this particular method. So I'll point you towards the paper in Physics of Plasmas last year, which goes into much more detail on the assumptions and the caveats here. But the results actually look pretty good. So we see the correlation is much improved. So this is now the distance from the shock in the x-axis and the prevalence of current sheets on the y-axis. And as we get further and further from the shock downstream, this seems to fall pretty nicely with a kind of power law of a -4 power law here. So that looks pretty good. That kind of seems to suggest, that kind of backs up that look, the result from the previous survey, which was showing that reconnecting current sheets are much more common at the shock, and then kind of sharply, the prevalence sharply decays downstream. But we can look at a few other parameters. This is the kind of the y direction, the y magnitude. So how flankwards are you in the magnetosheath? And you can see the prevalence of the current sheets kind of weakly increases. So there are more current sheets in the flanks than in the subsolar point, maybe. Compare and contrast that to a recent study by Stowers et al. In 2022, where they looked at the correlation length, that is sort of like a average spacing between current sheets, or kind of a turbulent stirring scale. And they showed similar, as you go further out into the flanks, the distance between, that turbulence stirring scale increases. So maybe those two statistics are related, and maybe that was simply our counting statistics get better where there are bigger structures in the flanks. So fewer current sheets escape our notice. But it's interesting that these this link here. If we look back now at our density as a function of shock parameters, we still don't really see any strong correlations here. It looks like, maybe this line goes up a bit, but I think that's just strongly weighted by these 1 or 2 points over here. So I want to say, there's no strong dependence on the current sheet prevalence for quasi-parallel, quasi-perpendicular shocks. So that's kind of the summary of these two surveys. They do mostly agree. We do see current sheets across all shock parameters. We see either slight dependence on shock parameters close to the shock, or further downstream, you don't see anything particularly strong. But in both cases, you do see a kind of a sharp drop off of current sheet prevalence downstream the current sheet. So we're nearly done now. I just want to highlight this study from 2021 by Schwartz et al., which asked the question, do those thin current sheets actually matter to the energetics of the system? And they looked at this, or we looked at this by kind of integrating up the J.E across each of the current sheets identified by a similar mechanism to the one I've been using in the study that I showed earlier. And they were able to show that about 11% of the bulk RAM energy incident at the bow shock is processed at those current sheets. So it's not a kind of a dominant factor, but it is a significant one nevertheless. So I promised a very quick return to simulations. So I will show you in the last 2 minutes a kind of a quick parametric study that I've been looking at, returning back to some simulations to see if I could recover why we don't see much dependence on the kind of the prevalence of current sheets based on shock parameters. So I don't think we need to be reminded of that. So what we did here is now just do a whole bunch of different current sheets, a whole bunch of different shock simulations across a range of shock parameters, Mach numbers in the range of 3 to 14, theta BN in the region of 10 to 80, and kind of quantify the reconnection that we see in those shocks and where it happens, and see what differences we get. And if we do that, we get some plots that look like this. In the short amount of time, I'll kind of skip over the mechanics of how we get to those. Suffice to say, we end up with this kind of top right plot is the important one. The blue line tells us how much reconnected flux we have in our shock simulation against distance from the shock. So you can see a lot of reconnected or closed field line structure in the ramp, and then it decays downstream of the shock here. And if you do that over a whole bunch of different shock parameters, kind of if you fix the Mach number at 7.5 and change the theta BN, you get the similar sort of downstream decay rates of those that reconnected flux. So maybe that goes some way towards explaining why there's so little variation in that survey. So I'll pretty much stop there. Here are the key conclusions, and maybe I'll just run through those quickly before we get to questions. Suffice to say, reconnection is a common process occurring in the shock transition region. It's most common adjacent to the shock, and then it kind of decays downstream of the shock. It's driven by either an ion fiber instability in the case of perpendicular shocks, or an ion-ion beam instability for quasi-parallel shocks. And it may have a significant impact on the energetics. So I'll stop there, and thank you very much for your attention. And I'm more than happy to take any questions you have.
Great. Thank you, Imogen. That was really great. We do have a couple questions. The first one is from Jerry Manweiler, and it's regarding the ratio of the proton mass to electron mass and how much that affects the simulations at the beginning of the talk, especially the more chaotic and turbulent nature, and whether or not you've investigated changing that ratio and how that might affect the simulations.
No, that's a very good point, and I think that is a fairly strong limiter towards getting, getting the simulations right, and part of the reason why you need to turn to the observations. Ultimately, a lot of the simulations that I've been personally looking into are hybrid simulations, essentially having infinite mass ratio. The electrons are treated as a fluid, and in that case, you can still generate some reconnection by that ion-ion beam instability. The full pig simulations that I also showed you, that was the kind of the Bessho et al. Paper from 2020, and the Matsumoto et al. Paper from 2015, had much more unrealistic mass ratios in a sense. Oh, I've gone too far now. The Bessho et al. One was, I think, 200, and I think the Matsumoto et al. One was similar. 200 for this, 225 for this. So yeah, it really kind of becomes non-viable to turn it up a little bit more than that. The computational resources become much too great. So I don't think either of these groups have pushed it much higher than 200. But I think it would have some effect, certainly on the electron scales, the separation of scales between the ion and electrons. But I don't know. There's not a lot of work being done on that to my knowledge yet. The field is young, as it were.
So I had a question about the parallel shocks, I believe. You showed the shock reformation.
Yes.
As it got turbulent and then broke down in scales. Is that something you can observe with MMS or possibly with a newer mission being launched?
So something like this.
Like helioswarm?
Oh, I can't wait to get a hold of helioswarm. Yeah. No, you're right. There is a real challenge in separating time and spatial structure. So you can see some signatures of shock reformation in MMS data, but you tend to move through these shocks at much faster, than an ion. A few ion times needed to reform the shock.
Mm-hmm.
So, for example, embarrassing typo in my slide here, reformation. So, for example, you can see signatures of shock reformation in this particular example, which was one reason why we chose it as a good case study. You can see this periodic increase or sort of downturn of the ion spectrogram here, which is associated with those kind of upstream shocklets that grow from the backstreaming ion population. So these are the ones that are eventually going to grow and grow and grow and reform a new shock.
Oh.
So you do see this kind of time snapshot of it, the kind of the upstream precursors. There is, you can see some amount of reformation as well when the MMS spacecraft turn to what we call a kind of string of pearls or a collinear configuration. Mm-hmm. So, once you have them in a line like this, and the separation is a few hundreds of kilometers or more, at that point, you'll see MMS 1 cross the shock when it's in a given state. And then when MMS 4 crosses it, it'll be in a different state. And you can see the changes in what the shock structure is associated with that reformation then as well. So it's challenging, but it can be done. And helioswarm will be even nicer.
Cool. Excellent. Well, that's all we have for today, but I'd like to thank you again for a wonderful talk.
Thank you all.
Next week, we do have a break for the long weekend for Independence Day. And then following that, we will have our next set of early career speakers. So I hope everyone has a wonderful week and a wonderful long weekend for those of you that get to enjoy it. And we'll see you all in a couple weeks' time. Thanks again, Imogen.
Thank you. Thanks for having me.